Today in this session, we will discuss on understanding the impact of alumina in blast furnace operation. Blast furnace rely on precise material balance to maintain efficiency and stability. Even a small changes in raw material chemistry can trigger significant operational consequences. Today we will explore how a 1%, only 1% increase in alumina can ripple through the entire process. So in the next slide, we have a detailed calculation and we try to see that a small but significant change can have a lot of impact. So let's consider a simple scenario. What happens if alumina in a ferrous burden increase by 1%? For our reference furnace, this translates to an addition of 15.7 kg of alumina per ton of hot metal, and this is we derive as you must be knowing, for 1 ton of hot metal production, if you are taking 1570 kg of ferrous material, then 1% of this will be around 15.7 kg alumina. This is how it is derived. Similarly, if a furnace has got a total ferrous unit consumed to produce 1 ton of hot metal is 1700, then contribution will be accordingly change, and it will keep on increasing, and this will result it to something 17 kg of alumina in place of 15.7. So this small change set off a chain reaction affecting slag chemistry, coke consumption, and furnace productivity. Now coming to, as it is already clearly shows the by the calculation, and so the goal in slag design is to maintain fluidity and control alumina concentration. Originally the slag received 33 kg of alumina per ton hot metal with added 15.7 kg, what we have seen in the our previous slide, and the new becomes 48.7. So total load has gone up by 15 by up to 48.7 kg per ton hot metal. So to keep the alumina concentration at the ideal of the same level, we must now have to adjust the slag volume accordingly. And when we adjust the slag volume, as it can show, to dilute the increased alumina and maintain slag chemistry, the total slag volume has to increase, and from the calculation now we need 366 plus kg of slag per ton of hot metal, up from the reference 250 kg, and we can say that that is a jump. On the in the previous slide we have shown that 116 kg per ton hot metal, and this increase often requires additional siliceous fluxes, which in turn demand more basic fluxes, adding complexity and cost of burden. So coming to our this slide, which already shows that how the coke rate is increasing, how the productivity is decreasing with the help of increasing coke. And this slide also summarize that when we increase our slag volume, our coke consumption gone up by 5.8 kg per ton hot metal, and which result into reduction of productivity by 0.58 ton per meter cube of inner volume. So here the IV signifies the inner volume. So now as we can see, it shows very clearly that using a conversion factor of 0.05 kg coke per kg of slag, the extra 116 kg which we have added now, that demand an additional of 5.81 kg of coke per ton of hot metal, and due to this increase in additional coke, the is directly affect the fuel cost and thermal load. And so we can say that productivity suffers huge For every 10 kg increase in slag rate, productivity dropped by 0.05 tons per cubic meter of inner volume per day. So with the 116 kg more slag, productivity decreased by 0.58, and that is a direct consequences of higher energy demand and slower progress kinetics. So the ripple effect, we can summarize that 1% alumina increase, we can say that slag volume increased by 116 kg per ton hot metal, and coke consumption increased by 5.8 kg per ton hot metal, and productivity dropped by 0.58 ton per meter cube inner volume. So a small change in body chemistry leads to a significant operational penalties, and we can say that this example reveals a crucial insight that even minor shift in raw material composition can escalate cost cost drastically increase due to increase in coke rate, and reduce output as productivity goes down, and this stabilize the process also. So higher coke rates means more fuel expenses, and lower productivity means less hot metal, and unstable slag chemistry risk tapping delay and refractory damage also. So the key takeaways, if we talk about, so it say that the meticulous raw material management is must for this, and this include a rigorous screening of fines, careful selection of burden material with controlled chemical composition. By doing so, we protect the furnace efficiency and ensure the process stability and maintain a huge profit